Hola, Miguel. Todo el problema del link estaba todo bien, porque me extraña que no haya nadie a esta hora.
Ahorita yo me metí a otro, creo que por eso no funciona. O sea, ahorita mejor les voy a decir eso.
¿Te metiste a otro?
O sea, había dos links. En el
Pues,
segundo
pues,
me metí porque el primero no funcionaba. Ya les
ah,
dije.
ya, ok. El segundo lo acabo de poner, pero pensé que era exactamente el mismo del primero. Yo voy a chequear. Aunque a la 1 de la mañana recibí unas alertas de que la sesión Zoom estaba por empezar como a la 1:15, así que quizás estaba mal la hora.
Ah, seguramente. ¿Me puede mandar el link, profe, por si acaso? ¿En dónde puedo ver?
¿Por dónde
Aquí
te
en
lo
la
envío?
invitación. ¿Por el chat?
Ah, ya te
Sí,
lo
es
envío.
que...
Aunque ya están empezando a entrar, ¿no?
Buenas tardes, profe.
Ya entra.
Buenas tardes, que hubo una confusión con el link, ¿no?
Sí, había dos links.
Ah, qué raro, porque yo pensé que los dos, el otro lo puse anoche, pero creo que se disparó a la 1 de la mañana. No, creo que es un error de Zoom, no sé qué fue lo que pasó.
Sí.
Salía que este estaba en otra
Seguramente
meeting,
era
o sea,
yo.
estaba en esta.
¿Perdón?
O sea, estaba en esta meeting usted.
Ajá, ok. Bien. Bueno, espero que todo el mundo se dé cuenta entonces. Si no, les puse el link abajo en el chat por si pueden enviárselo a cualquier compañero que no se logre conectar. Vieron que vamos a hacer unos webinars. Empieza julio el jueves y vamos a tener 1 o 2 por semana.
¿Qué es eso? Un webinar
Un webinar es un seminario por el web.
online.
Va a ser va a ser por Zoom.
Ah, ya. ¿De distintos temas?
¿Perdón? Sí, sí, entonces van a
De
tener
los
temas de física, de biología, de química, de todo, de todas las áreas.
Sí, acabo de
Ya.
ver el correo.
Ajá.
Recién lo mandaron.
Profe, ¿y se habló con los profesores sobre el tema del semestre? ¿Me
Sí,
puede
sí,
entrar?
correcto. Ya al mediodía tuve una reunión con ellos después de haber tenido una reunión con todos los decanos y entonces más o menos recorrimos los puntos de los, por lo menos química y física tenían unos informes sobre las vicisitudes de la semana anterior y entonces creo que quedamos todos en la misma página con el tema de bajar la velocidad, digamos, considerar la situación de los estudiantes que no tienen quizás el ambiente más propicio para oír las clases y entonces creo que quedamos todos de acuerdo, ¿no? De que había que aprender a usar las herramientas y ir mejorando la interacción y tomarlo con un poco de calma. Pues yo creo que ya es, digamos, más o menos claro de que vamos a tener que prolongar el semestre en base a una evaluación al final de este problema y de manera que entonces cubramos la materia con calidad, pues, ¿no? Para los estudiantes. Entonces, ya eso está claro. Entonces, incluso se manejaron varias otras herramientas que están usando otros profesores como Google Classroom y otras herramientas de dibujo para escribir, por ejemplo, ecuaciones con látex en, este, en las sesiones de clase y ese tipo de cosas. Así que yo creo que todo el mundo obtuvo algo de la reunión.
Ya, profe.
Chévere. Ustedes ven, digamos, que alguien ha estado faltando sistemáticamente a las clases para ver si lo podemos contactar y yo la verdad es que no me he dado cuenta y creo que no tengo registro de quiénes estaban, pero debería ser
¿Alguien
eso.
de este curso? Yo no he visto. Sí, creo que llega. Son
Ismael,
como-
profe.
¿Perdón?
Ismael Villegas, él falta porque no tiene internet en su casa.
Ah, no tiene, o sea, no ha estado en ninguna de las clases.
No, él realmente estaba poniendo de su dinero para comprar datos, para poner saldo en su celular y a través de su celular él trata de conectarse, pero
Ah,
casi nunca se conecta.
me dijiste Ismael
Villegas.
Villegas. Ok. Y no, digamos los demás, los otros estudiantes vienen a algunas sesiones y otras no. De todas maneras, todas las sesiones están grabadas. Así que, no habría problema. Bueno, empezamos la clase entonces, ¿no? Espero que se unan los que faltan en unos minutos. Yo creo que desarrollé una o dos destrezas más desde la última clase, así que vamos a usarlas de inmediato. Entonces fíjense que ya sé poner la tableta del tamaño que quiera y además de eso logré también reducir el tamaño de la punta de escritura para que las ecuaciones no salieran tan gordas. Ok, entonces hoy vamos a hacer algo que digamos, ¿y qué pasó aquí? Falta la conexión. Eso. A ver. Ok. Entonces, hoy vamos a hacer algo que... ¿de qué modo está esto aquí? Ok, que yo considero como una sesión de ejercicio, ¿no? Sin embargo, vamos a tener una sesión de, así como exclusivamente de ejercicio. Vamos a revisar la tarea mañana para ir punto por punto a ver si ustedes reconocen, digamos, los problemas que están ahí. Y así que esa va a ser la sesión formal de ejercicios de esta semana, ¿no? Hoy va a ser una mezcla entre ejercicios y continuar un poco con la materia, ¿no? Porque tenemos que ahora empezar a hacer cálculos en serio, ¿no? Entonces, el primer punto era connect. Green's functions learned before with a current formulation. Okay, so I think you will remember this first way of stating the Green's functions approach. So remember that you had some kind of an operator before. So that could be a differential operator applied to some function that depends on space and time. This could be a vector quantity. And it was this in general can be an inhomogeneous equation. Okay. So the Green's function solution to this problem was given in terms of the same operator applied to the Green's function, which is now a function of x minus x prime, okay, and t minus t prime, okay. And the solution to this, so you apply the same operator in both cases, okay. And now this was equal to delta function x minus x prime and delta t minus t prime. Okay. So I'm using the same notation here because this is the old and current Green's function. Then we're going to show that today. That's the same function. Okay, so how do we prove this? Well, we do this on the integration. If we integrate now the operator, and remember this operator acts, okay, acts on x and t, okay, not on x prime t prime, but on x and t. Okay, so if we integrate now the differential operator applied to the Green's function, x minus x prime, t minus t prime, this multiplied by f of x and t prime, both dx dt prime, okay? Then this should be equals also to the integration of the other side of the equation, okay? So we have delta x minus x prime, delta t minus t prime, okay? Multiplied by the function x prime t prime dt dx prime, okay? So we just multiplied from the left, okay? From the left, right? From the left, this equation multiplied by f and integrated over the x prime and t prime variables on both sides, okay? So we get this equation here. Okay, so now this side of the equation we can solve, right? Because this just involves two delta functions. So this is going to be equal to f of x and t, okay? So this is one side of the equation. And on the other hand, this is equal to, using this first equation here, to the differential operator applied to the function. This can be thought of as a wave function in quantum mechanics, so this can be thought of an inhomogeneous Schrödinger equation, for example, okay? So this would be now the corresponding equation for the Green's function, which now has an inhomogeneity, which are just delta functions, okay? We integrate both sides, having multiplied both sides by f, and integrate over all the range of t prime and x prime, and then we get this. So now we get this expression here, and notice that this operator here operates on x and t, okay? So we can take this operator out from this equation here, okay, because it's not involved in the integration, and we get this here. Okay, and this is equal to the differential operator, whatever it is, x and t. So you see now this expression here is very interesting, because now we have the same operator on both sides, okay? So they're operating, the differential operator operating on x and t, and not x prime and t prime, which are going to be integrated over. So now we can identify in the following that psi of x and t can be written in terms of the integral of the Green's function minus x prime t minus t prime, okay, x f of x prime and t prime dx prime dt prime. So you see that this is now the solution to the problem. If we can solve for the Green's function, then we can solve for the wave function, okay? Any questions about this? Is it clear what we did here? Okay, so we started from the differential equation we want to solve, okay? And then just wrote down this, the equation for the Green's function with the same operator here, the same differential operator, but where the inhomogeneity was a delta function, okay? So, so this, I claim this G, and we're going to prove this, is going to be the way you learned this in Mathematical Methods 1, okay, the Green's function. And it's going to be exactly the same function we're treating here. So we multiply both sides by the inhomogeneity of the original equation, integrate both sides, and we get this relationship that we have here. So formally, this is a solution here in terms of the Green's function. So you see that if I have the Green's function, I have the wave function, okay, once we integrate this. It turns out, and we can go over the details of how, what kind of a limit this is, but this is a singular limit of this previous treatment, that if we have, and now we're going to be a little more explicit, if we have now the differential operator we're interested in, which is our regular kinetic energy of the Schrödinger equation, and we have our time derivative, okay, this applied to the wave function, okay, this equal to 0, then the same type of solution applies, okay. So we have to make a analysis of the singular behavior, what happens when I have 0 instead of f here. But the claim is that we can use exactly the same Green's function, okay? So we have the same differential operator plus I d dt, now applied to the Green's function, which has these arguments here, and this is going to be equal to, will also be a solution to the homogeneous problem. Okay, so bear with me for a second about this this case of the homogeneous. I'm missing a U, homogeneous problem. Okay, so I claim that we can start with the same form of the Green's function. Okay. And now I'm going to illustrate this in Fourier space, okay? In Fourier space. So what do we do in Fourier space? We define the Green's function, and you know, if this course serves for anything, it should serve you for you to remind you of or even generalize some of the things you've seen in your previous courses. Okay, so this is the 3D Fourier transform. This is the spatial transform. Okay, G. So I'm going from xk space to kt space. Okay, so this is the definition of the Fourier transform. So now that I can introduce this Fourier transform here, okay, in this expression, we've done this before in class, so we get the integral dk3 and then minus h squared k squared. So you see that if I put I operate with this differential operator, go into this integral, right? So this differential operator operates on anything depending on x. So it can go in, this is an integration over k, and then this depends on x, so it lowers two factors of ik. So we have minus k squared, right? So just from this differential operator here. And then we get the plus I, and there's no time dependence, no explicit time dependence there. So we get this, and we get a g of k t minus t prime. Okay, e to the I k x minus x prime. Okay, on the other hand, we can use now the integral representation of the delta function. So the integral representation of the delta function will be integral of dk cubed e to the I k x minus x prime. Okay, and we use just a regular function as is. Okay, so this delta function I leave alone. So this is not integrated. We can put the delta of t minus t prime inside or outside the integral. It doesn't matter because there's nothing to be integrated here in this integral. Okay, but now you identify here we have the same factors on both sides. Okay, exponential. We have this differential operator applied to g. Then we have the integral here. So we can identify now an equation in Fourier space. So in Fourier space, okay, in Fourier space, and here I refer to Fourier space, but this is really a partial Fourier space because we're going from xt to kt, right? So this is what we're really doing. So this can be.
Teacher, can you repeat the part of the application of the operator in the integral in the previous?
Okay. So what did we do here? So we have this differential operator here, and this function in xt space. is going to be written now as an integral over, okay, over the Fourier transform of this Green's function, right? So now we push these operators against this integral here, right? So they both go through. We can take the derivative inside the integral here because the integral is over k, and this doesn't involve any k. And this is also can be pushed inside because this is taking the derivative with respect to x, okay, which is a fixed variable inside the integral, you see? So these are just the,
Yes.
okay, so we can take a derivative inside the integral. It doesn't affect anything, the case, but it affects this, and it doesn't affect in any way the Fourier transform. It doesn't depend on x, okay? So it only takes a derivative of the
Okay.
exponential, okay? So it brings down
Yeah.
2 factors of I and 2 factors of k. So this is what we have here. 2
Mhm.
factors of I
Yes.
give us a minus, and 2 factors of k squared. And the
Okay.
time derivative just, you know, doesn't do anything, okay?
Mhm.
Okay, so this is the equation we have. And so I clarify this, that we're going from xt space. So this is sort of a partial, a complete Fourier transform would be going, okay, complete would be going from xt to kw, okay, k omega, okay? Okay, so in Fourier space, we can identify the equation is now we lost the differential operator here. We just have 8k squared over 2m plus I partial of t, okay? And this will be the Fourier transform or the partial Fourier transform of the Green's function, okay? Equal to delta t minus t prime, okay? So there we have it, okay? This would be now the equation we have to solve, okay? Instead of solving this equation, we're just going to see now that this is actually, and notice that this is just the free Schrödinger equation, free Schrödinger equation, okay? That is what we normally call H0 because it just contains a kinetic energy, and this is a time dependent, which is generally what brings down a factor of the energy. So this would be the time dependent version of the eigenvalue equation associated with H0, okay? So what should be the solution of this equation? Well, it should be, one of the solutions should be G naught plus, right? This will be the free Green's function associated with this Hamiltonian here, okay? Really, this is the Hamiltonian. This is because the Schrödinger equation would be H0 applied to psi is equal to minus I d dt psi, right? So this would be the Schrödinger equation. Okay, so what is the solution we had obtained before for this free Green's function? It was, and I just recall from the previous classes, I minus I theta t minus t prime e to the minus I sub k t minus t prime. Okay, remember? Okay, so we had obtained this this solution for the Green's function, and I want to show you that this is actually the solution to this equation here. Okay, so this is the way we're going to make the connection. If this is the solution to this equation, then we make a connection between the two approaches. Okay, okay, if G naught is solution, then we connect both approaches. Okay? Okay. Okay, so let me make some remarks before starting on this. Let me start to write in black. Okay, so let me make here just if zero is a solution, then we can connect with approaches, okay? So let's show this. So in order to show this, we have to establish some results first, okay? So remember that the theta function of x, we could also write the theta function of x if this is a continuous variable, okay? Was this function here. So if x is positive, let me put it like this, x is greater or equal to 0, this was 1. If x is less than 0, is 0, okay? So this is a step function going like this. Let me just put it just above the axis here, and it jumps here to 1, okay? This would be 1 here, okay? Okay, so let's take the derivative now of that function. So let's see, dx of t. So we know how to do, for example, we need to take this derivative here. So if we substitute this solution here, we wouldn't have to know what the derivative of, with respect to time, of this function is, okay? So the derivative of this is going to be the delta function, okay? How do we know this? Well, I don't know if you find this intuitive, but I mean, this has a jump, so it's a singularity. You can sort of see this by sort of making an approximation to that function, assuming that it doesn't have infinite slope at a particular place. So if you assume that something like this is happening, okay, this goes to slope 0, okay. Let's sort of make it symmetric, and some finite slope, and it goes to, okay. So let's suppose this function here is just the limit in which this is a finite slope. So it goes from 0 and then assumes a finite slope, and then it goes from this finite slope to 0 again. So if we take the derivative, okay, if we take the derivative, okay, this will be something like this. So the slope, okay, the derivative is 0 here, and then it assumes a finite slope, and then it goes back to 0. Okay? Let me, so if we have this is assuming that we have some smooth transition here, right? So this may be something we could put like this. So we have some smooth transition, like going like this, and then going like this. This would be sort of a physical function, right? And this would be this transition here, okay? So we'll make a smooth transition in both places, then we have something like this. And this, in the limit in which this slope becomes vertical like this, becomes a delta function. So this grows and grows, it goes to infinity at one point, and then goes to 0 at the other point. So this will be the delta, okay? Is this clear? So if we take the derivative of the step function, we get a delta function, okay? Okay, so this is one result we're going to use. The other result we're going to use is that if we have a function, any function, multiplied by delta of x, okay, this is going to be exactly the same as the function evaluated at 0 by the same delta, okay? When we have these functions here, these deltas are called distributions. This is a whole field of mathematics. Okay, these distributions are the algebra of these distributions is done makes for equivalences under integration. Okay, so is this true? Okay, is this true? Okay, so this is true only if this equality is preserved under integration. So if we integrate both sides of this equation, okay, dx is the same as this. Okay, and is this true? Is this true? Well, let me put it here. Let me make it a little nicer here. Okay. Okay, so is this true here? Okay, you know this is true because, okay, so if this integration range here includes x equals to 0, then this is the only point at which this is going to be non-zero. So this is going to be f of 0. And this is the same for this because this is a constant, so I can take it out. And the integral of the delta function over dx is just 1. Okay, so f of 0 is equal to f of 0. Okay, so according to a theory of distributions, of which the delta is part, okay, in the theory of distributions, we can also contemplate derivatives of the delta and so on, okay? But in this case, these two expressions are the same if under integration they're the same, okay? So we just integrate them and verify that actually this is an identity, okay? Is this clear? So these two tricks we need to use here, that the derivative of a theta function, okay, is a delta, and the other one is that the product of f times the delta is equal to f0 times the delta. One final thing about the theta function, okay, is that remember that if I have now the theta function of t minus t prime, so this just shifts the previous definition, okay? So this is the t-axis. So now we have t prime here. So when t is greater than t prime, the argument would be positive as a whole. So we will have that this is just a set function here. Okay, will be 0. Okay. Okay, so knowing this, now we can face this substituting this solution into this equation here. Any questions before this? No, everything's fine. Okay. Okay, so let's continue with black. This. Okay, so let's substitute. So I'm just here going to operate. So the first term in the operator. So let's sort of see here what we're going to do. So first we have to multiply whatever function this was. So multiply by this because this is no longer a differential operator here. So we just multiply by this function here, and then we have to take the derivative. So we have to take the derivative first of the theta function. So we use this trick here and leave the exponential alone. And then we leave the theta function alone and take the derivative of the exponential, okay? So that's what we have to do here, and let me write it, and then we'll go back to the equation to see if I wrote everything correctly. So if we have here in Ibarra, we're supposed to be in complete lockdown from 2 o'clock, and you see the traffic outside, right? Okay, so we have this prefactor here, and we have just write the Green's function, t minus t prime, e to the minus e to k t minus t prime. Okay, so this is the first term, and then we have the derivatives. Okay, so I just taking out the I term here, right? So we have an I here in this expression. So I just write the I, Okay, and this is multiplied now by minus I, which is the part of the Green's function, the derivative of theta, which is delta t minus t prime, okay, and then the exponential. Okay, this is the first term, and then we write again, and this is the continuation, so we get minus, okay, minus I theta t minus t prime, okay? Then we take the derivative of the exponential, so we get minus I, okay? We derive with respect to t, so we get minus I, and then we get the energy, and this expression, this is just the energy of the free particle, and then we get back the exponential. Okay, so perfect. We close the parentheses here, and this is going to be what on the other side? This is going to be theta of t minus t prime. Okay, which is the other side of this equation here, theta delta t minus t prime. Okay, so let's do an inspection of this problem. Any problem with this derivation here? Does anything need any clarification? So now let's see what we have here. This is the free particle energy. So this is h squared k squared over 2m. Okay, so we have here the same factor as we have here. We have I times I minus 1. Minus minus is a plus, so this is has a full a minus sign. Okay, minus minus plus. I is a minus 1, so this is minus I, and here I have plus I theta. Okay, so this term is canceling completely with this term here. Okay, and then we get, so I times minus I is just a delta t minus t prime times e to the minus I t minus t prime is equal to the delta. And this is obvious, right? Because the delta is going to, this is again an identity that is equal under integration, but we can think of f of t minus t prime, okay, times the delta. So we use a second trick that I showed you. Okay, so this should be the same as delta of t minus t prime okay, times f of 0. Okay, and what is this? F of 0 is the exponential evaluated at 0, so this is just 1, so this is delta t minus t prime times 1, and this is equal to delta t minus t prime. Okay, equation satisfied. Okay, so the Green's function we wrote before is exactly the solution. So the solution to the free particle propagator that we had derived before is the solution to this equation, okay, which is the previous version of the Green's function we had learned in Mathematical Methods 1. Okay, is this clear? So now we have a connection between the two, the Green's function we're talking about right now and the Green's function you have learned about in a previous course. Okay, is this okay? Any questions here? Is it satisfactory, this derivation?
Yes.
Okay, okay, so it is clear. Okay, so now let's derive the second part. The second part of the connection is going to be this expansion, this Dyson expansion. Okay, so connection with Dyson expansion. Okay, and this is going to be fun. For example, let's focus on on the potential we had before. So remember that we had this potential before that we were working on, which was particularly simple and allowed us to obtain everything exactly. Okay, so let's suppose we start with our differential operator, now with a potential. Okay, so we have this differential operator, we have the time dependence, okay, and we have this potential that is only depending on nabla. Okay. So this is again an homogeneous equation. Okay. And for example, we're assuming here I put V nabla because this is just a function of the momentum operator, right? So this was the previous potential we were working with. Okay, so now we included that this will be a single particle interaction, okay, which we have been dealing with until now. So hopefully the second part of the class we will see that we will see now the two-body interaction, but this is just a single particle interaction. This will be now, this plays the role of the L0, and this will be now the interacting differential operator. So this will be, let me pull this. Okay, so all this with the interaction will be the full differential operator applied, and you see this is also differential, so this is a full differential operator in space and time. Okay, so so this will be an equation, and now we write the equation for the Green's function. Okay, so now this will be, this is an xt space in kt space. Okay, we have plus I t minus v of k. All this differential equation, the differential operator only depends on nabla, so any factor of nabla operates on the exponential, and we get a dependence on the wave vector. Okay, this applies to the Green's function now in this half Fourier space. Okay, and this will be my full, okay, full interacting Green's function. Okay, so this in principle is the you know, this double arrow that we had before. This is the fully interacting propagator. Okay, and this is going to be equal to delta t minus. Okay, so what does Dyson say? So what we're going to do is now, the strategy for proving the connection is that we're going to start with the solution, a Dyson solution, and we're going to derive this equation here, okay? So we're going to begin, okay? So we begin with Dyson solution and derive equation above this one. Okay, so let's do that. So what was Dyson's solution? Okay, now in terms of the Green's function was, let me write it here neatly. So this was k t minus t prime. The full Green's function was, in a first approximation, was the free propagator, okay, plus the integral between minus infinity to infinity. Let me put here 2t double prime to distinguish it with the other variables. We get the free Green's function, which is a function of t minus t double prime in this integral, okay? And then we have the interaction, which is this one that we have here, the same interaction. Okay, and then we have, this is sandwiched with the full Green's function, g, okay, of k t double prime minus t prime. Okay, so this is Dyson's equation. So remember that this function here is the same as this function here. So remember that this, just to remind you in terms of the diagrammatics, which you might remember better, remember that this was, this guy is equal to this guy, and then we had plus the propagator corresponding to this, okay? Blob, whatever, L, M, and then we had the double propagator, okay? This was a way to make it compact. So this was the Dyson equation in terms of diagrams, okay? Okay, so now let's convert this equation here into this differential equation here, okay? Is it clear until now? Okay, we have this, and now I'm going to apply to the right of this equation. I'm going to apply the free differential operator here, L0. Okay, so I'm going to apply it to both sides. Okay, so we get this applied to G plus. And let me put all the arguments so that we're clear in the beginning. So t minus t prime is equal to, okay, t minus t prime, okay, and then apply the operator. So remember the operator, this operator here, is operating on space and time, okay? So this is this is the L0, so it operates on space and time, okay? So now we apply it to the integral. So that, what's the integral going to look like? Let me make some space here. So we applied, we can introduce it inside because this is being integrated, so over t double prime. This is integrated between minus infinity and infinity, and then we get this applied to g naught plus k t minus t double prime v of k, okay, and g 0, not 0, g plus k t double prime minus t prime. Okay, so you see this differential operator is operating on the unprimed variable t, okay, and on this vector here, okay, and nothing else, okay. So okay, so I apply to the right here. Let's see. Yes. Okay. Oh, okay, so this is acting on space, okay, space and time only. So this is what we have. Okay, so I was confused for a minute there. So this is acting on space and time only, not on k and omega. Okay, so just in space and time. So this is actually acting only on this guy because these guys do not depend on anything related to space and time. Okay, so So we just substitute what we know for this. So we know what is this equal to. We just proved it here, right? In this exercise we did here. So this would be the free, okay? This will be here, what we have here. And the solution to this is exactly G0 plus. So this applied to G0 plus is equal to the delta. So we apply that result here. We know that this is just delta of T minus T double prime, okay? And this is going to be delta of T minus T prime, okay? So good, so we're in business. So if this is the delta, we can straightforwardly do this integral because you see we have T double prime here, which is the integration variable. So we just apply the delta here, and this will give me what? This will give me the free differential operator applied to the full Green's function, okay, and T minus T prime. This is going to be equal to delta of T minus T prime, nicely, looks like a plus sign, T minus T prime, okay, plus V of K, okay, times the Green's function, evaluated at a T double prime equals to T. So this was T minus T prime. Good. Okay, so now we just have to put this on the other side. So we have now that the free differential operator minus V of K times the full Green's function is equal to the delta. Voila. Okay, so here we have the previous expression. Here we have exactly this expression here in a Fourier space. We have derived this expression from the Dyson expansion. Good. So this gives us, okay, equivalence between Dyson expansion and old, okay, Duncanian Green's function. Okay, any questions there? You know what Duncanian means?
What? Because
Duncanian.
Duncan
Right.
teaches that.
Right. So this is the old Duncan version of the Green's function. You see that it's exactly the same that the one that we're using here, but this is just the sort of the integral equation version of the for the solution of the Green's function. Okay, so it's the integral equation solution to this differential equation. Okay, so this is essentially the connection I wanted to make, so that you see that there's unity in what you've been learning. Okay, so just to close this a bit, remember that this form of the Dyson form was exactly the expansion that generated this expansion for the Green's function, where the G plus K and T minus T prime was equal to at first the free propagator T minus T prime plus, okay, integral minus infinity to infinity dt double prime G0 plus K T double prime and V of K, okay, G0, okay, T double prime minus t prime, okay? And then you had the other term, okay? So we have a double integral now, minus infinity to infinity, dt double prime d double prime dt triple prime, okay? G naught, and I here omit the arguments for, okay, b, and so on. Okay, so remember that how we could generate this from, okay, so this is the, in diagrammatic form, this is equal to the free propagator plus free propagator below free propagator plus free double, and so on. Okay. So now, okay, so many of you maybe just feels better with this formulation here, and then going to the integral. Okay, so here in the integral you have to remember lots of things to write this down. But then you have the Feynman rules. Okay, so the Feynman rules, Feynman rules. Okay, and then you can translate diagrams into the full equations. Okay. So this is the end of the first booklet, my notes, okay? And we go on to the next one, okay? So now things are going to get interesting and we're going to see the butter on the toast. So why do we learn all this? Okay, so I would like to go back to a previous expansion we did. Okay, so let's make a summary. Okay, so the summary is that I'm going to express Green's functions in two different spaces that we have addressed. So this is going to be KT space. This is going to be K omega space, which is where we should be working all the time because it's an algebraic, okay? So this is completely algebraic. Well, this is a integral. Okay, remember that when we have the time, we have to integrate over all the possible times in which the interactions occur, and this all disappears, all these integrals disappear in K omega space. And everything becomes algebraic, and we like algebra. Algebra is easy to do, okay? So in KT space, we have then the Green's function. This is the fully interacting Green's function. So we have K2, K1, T2 minus T1, and this is represented by the double propagator line, and we get on one edge K1, T1, on the other K2, T2. Okay? We also have the whole interacting propagator, although we haven't done any exercises with that one, just with the free hole propagator. So everything here is going back in time, and so everything here is going forward in time, except for the virtual processes, and I'll explain in a little while what I mean by virtual process. Okay, T2 minus T1, and here we have again this arrow pointing now in the other direction, where we have K2, T2. Oh dear, much noise. Sorry about that. Okay, now we got the free propagators. 0. So I live right on Atahualpa Street, so you can imagine this is the busiest street in Ibarra. So we have K, T2 minus T1. Okay, so this is the free propagator. This is just written by the simple line going with the same arguments I have here, except that we have a single k and 2 time arguments. Okay. This is also equal. Let me put it here just to theta t2 minus t1. So this is a full rule book. Okay. Now I'm going to put a new rule which was sort of assumed obvious in the previous treatment. I'm going to put that every time you have a free propagator, that is propagator going to the right, we have an energy that's greater than the Fermi energy. Okay? So now this gets multiplied by e to the minus t2 minus t1. Okay? So this is the full expression for the G naught. Okay? And we have almost the same expression for the Green's function with a minus, okay? Which is a function of k and t2 minus t1. So we can basically copy everything here, except that we have a theta of t1 minus t2. Okay, so this is 0 in the complementary range. And we also have that when we have a negative here, we're assuming that the energy we're referring to is below the Fermi energy. Okay, times the same exponential here. So let me lift the skirt a bit here. Okay, and a T2 minus T. Okay. Okay, so that's in KT space. In a K omega space, the expressions are a little more comfortable. So we have I, G plus, okay? You can refer to K2, K1 now, and omega. Not so many expressions here. This is a double line propagator with omega now, K1, K2, okay? And then we have the G minus of the advanced propagator, this is K2, K1, and omega. This is the propagator propagating backwards, K2, K1, okay? And then we have the Fourier transforms of KT space, okay? So I have I, G naught plus, okay? So we're going to use these results. And now this is going to be equal to I theta, so we copy the same restriction, the same theta function we had before, okay, over omega minus epsilon of k. And this is plus I delta, okay, so this plus corresponds to this plus here, okay, and this is the full expression, and we have that this is going to be the propagator between K1. Okay, so here I just put it in general, so K1, K2, and omega. Okay. Actually, I should not put two arguments here. I should let me correct this. So this is the free propagators. I just have a single K, as I had before. Okay, so this should be this will be K omega. Okay, and then we have the IG 0 minus, okay, and omega would be I, and we switch the theta function, so now we have the Fermi energy is bigger, okay, than the K's we're dealing with, the energies, and omega minus E sub K minus I. Okay, this minus being corresponding to this minus K. Okay, we just need another sign for this, you know, regulates the integrals. Every time we get in trouble with the integrals, we invoke this factor here, and this makes the integral converge. So this we need always, okay? This is a convergence factor, convergence, okay? Which makes sense of the integrals that are ambiguous, but it also has a physical meaning, as we said before. This is going to be, in general, the lifetime of the particles. If we can take it to 0, then the lifetime of the particles is infinite. So we have our quasi-particle is a real particle, okay? Otherwise, it's a quasi-particle. It has a certain lifetime, so it decays in time. And then we have a finite value for this delta, okay? And a finite value for it. And finally, okay, so one particle operators, which we have been using until now, ops, okay? We have, on the one hand, let me make here is a KT space and K omega space. In KT space, this is minus I V K L, okay? So this is minus I, the matrix element between K, V, and L, okay? And in K omega space, we have V, K, L. This doesn't change, okay? So this is exactly the same. This isn't acted on by the transformation between KT space and K omega space, so we have the same value. But the important thing is that VKL for the one body operators, just this sandwich here, this matrix element that we have here for the one particle interaction. Okay? And this, remember, was this blob that we were using, we were talking about. Okay, so let's see. So let me put here, might be boring to write all this right at this hour of the afternoon. So let me go on to now two particle operators, okay? And we'll address the point in tomorrow's class. So I remind this in tomorrow's class. Okay, so I wanted to write, what I wanted to do is use all these rules to explicitly write the expansion we did in last class with the particle whole picture, okay? But we'll do it in the exercise session tomorrow, okay? So let's just begin the two particle problem, the two body operator problem, okay? Which is going to be the Coulomb problem, okay? So let's go to a new view graph. Interacting Fermi system. Okay, so until now, we have addressed only Fermi systems under external electric fields, external fields in general, okay? So now we're going to consider electron-electron interactions, okay? i.e. EE interactions, okay? So in order to consider electron-electron interactions, remember we need a potential now that has two labels, two position labels. So the Coulomb interaction was this one, all right? So I have two position labels. So now this is a two-body interaction. Okay? And so now we use an insight that that we mentioned before, which is that this operator here, okay, so this is going to be an operator, depends on two variables, is, okay, is translationally invariant. Translationally invariant. Okay? So this means that if this is translational invariant, okay, this means that, what does it mean when something is translational invariant? What is preserved? Anybody remember?
Momentum.
Momentum, correct. Very good. Okay, so momentum is preserved. Okay, P is preserved. This implies that the P, okay, equals to HK, okay, is a good quantum number. Okay, so we know that if we go to Fourier space, this is going to be ideal because we're going to be able to describe this operator in Fourier space very nicely. Okay? Although there may be some K dependence which is non-trivial, we know that when we go to Fourier space, we're going to have algebra again, which is the important thing. Because algebra, we know how to deal with, okay? Integral equations are just a mess, okay? So, okay, so the other thing we're going to do is we choose a basis from here on, choose basis, okay? Although we know that we have choices, we can have the free particle basis, we can have the hydrogen basis or hydrogenic basis, or we can have some the block function basis, etc. Okay, we have to choose one of those that we know, but here we're going to choose for simplicity just the free particle basis. So the free particle basis are the plane waves. Okay. Yeah, plane waves, this is very nice here, and the eigenvalues associated with the plane waves are just this guy here. Okay? Okay, what else is going to be new? So before we had, remember the interaction, okay, single particle, okay, was represented diagrammatically by this blob here. Okay, there was a little blob, and as I told you, it had two handles. So the two handles could be either on this side, okay, remember, so this was particle-particle interaction, where we could have something like this. We could have something coming in. So let me put the arrows. So particle-particle, it could be particle-hole, because it goes in the other direction. Or it could be, okay, whole particle, okay, or whole. Okay, so all these possibilities we had here with the interaction. Okay, and this, notice that the single particle has only two handles. Okay, the handles are the places where I'm going to insert the propagators, the free propagators. Okay, so this is just one particle coming in, interacting with the external field, and going out with possibly another momentum. Okay, so this we had before. So we had, if we attach the propagators, it was coming in with a K1 and coming out with a K2. So only just a single particle involved here, and this is the blob is the action of external field. Okay? Okay, so now we're going to make an Olympic somersault here. Okay, two body interactions. How do we represent them? Interactions. Okay, how do we represent them in terms of the diagrammatics? This you may have seen now in the literature, mostly from particle physics. Okay. So we're going to have, how many handles do we need? So we need handles for particles coming in. So two particles now are going to come in. Okay. Two particles are going to have to come out. Okay, because the particles are fermions and they cannot disappear. Okay. And they're going to be joined at a certain place. So the particle, these two particles are coming in here. These two particles, I don't like this drawing. Let me draw it again. So we have two particles coming in. Okay. And then we have two particles coming out. Okay. So these two particles may be in, for example, in the state K, M and N, and they come out as K and L. So this is just a diagram where you show some interaction between those two particles, and then you can show here, you can choose here any type of line in the middle. Okay, so this is representing the interaction now. This is a two-body interaction. And you see we need four handles. Okay? And this, in the literature, this appears like this, or sometimes some other authors choose something like this. Okay? Or like this. Okay? Depends on your artistic choice. You can put whatever you want. But what this is meaning, that this is some intermediate particle. Okay? Intermediate particle. Okay, it could be, in the case of the Coulomb interaction, it should be something like what? Anybody remember what's the intermediate particle of the Coulomb interaction? So the intermediate, the two particles are going to interact via electric fields. So the electric fields are made of photons. Okay, the photons are the vehicles for this interaction here. Okay, if, for example, we were addressing, so electro as intermediaries the photons. In superconductivity, which is an emerging phenomena, superconductivity, anybody adventure what the intermediate vehicle, the intermediate particle is in superconductivity? So electron interacts to another electron via a phonon. Okay, so this is not an elementary process like this, but this is an emergent process where two electrons interact via the lattice through a phonon. Okay, so this is another diagram we could draw in the theory for superconductivity. Okay, and then you have, for example,
Mr.
Yes.
Sometimes I read like Muse, like T process or mu process in literature.
T process? No, you have the sort of the, I mean, the process we're talking about is that you have two particles. For example, here are the two fermions. They're going to be electrons, so they're charged, so they interact via electromagnetism. Okay. For example, inside the nucleus, then you have other intermediate particles between quarks, for example, or the nucleon. So you have the nuclear, the strong force and the weak force. So you have the zeta bosons, okay? Or you have gluons, okay? Okay, so these are going to be, each force has an intermediate particle that is the one that's the vehicle of the interaction, or in terms of which we can quantize the strong nuclear force or the weak nuclear force, okay? So this is exactly the same in condensed matter, but I don't know what you were asking about the T particle?
No, I because I read sometimes like a mu channel process or T channel process, I think.
T channel, a mu channel?
Yeah, when you read about the Feynman diagrams and diagrams like the sometimes say the mu channel process diagram, and it's very similar to the diagram that we have in the two-body interaction.
No, send me this article to see, or whatever you read it to see what they're meaning, because I
Okay,
don't,
I'm gonna send you.
maybe it's some language in a particular field. Okay, so we have now this. We have to clarify now this. This is going to be the interaction. So this, instead of having a v of two variables, we're going to have a four labels K, L, M, N. Okay, so in the Feynman rules, we're going to put something like this: minus I over 2, and this is going to be now represented by this diagram. So every time we have this diagram in the Feynman expansion, we substitute it by this in the mathematical expression, okay? And the expression for this VKLMN we had seen before in second quantization. In second quantization, we need this to write the two-body interaction. So we're going to have that this is equal to phi of K R phi of L R prime. And then we have in particular, the Coulomb interaction, okay, which is a two-body interaction. And then we have M R N. Okay, so now you see it's a little more complex, okay, than the previous just one body interaction. So we need two bodies. So these are going to represent the states of the, and let me put it here. So this is this MN, the incoming electrons. These are going to be the outgoing electrons. Okay. So remember, this is in, this is out. Okay, and see that this is precisely what we have. The MN are going into the interaction, and K and L are going out of the interaction. Okay. So let me just draw as a last thing we do in this class. Let's just draw here something we have to take into account in order to draw the simplest diagrams that we're going to choose. So we're going to always use the particle hole picture, okay? Particle hole picture, okay? So in the particle hole picture, you can have something like this, so like the one we drew before. Okay, so here we have, okay, let me just label the diagram. So M, N, K, L. Remember that all the arrows here are, this is the positive direction. Okay, So we have that the energy of the particle is going to be above the Fermi energy. Okay, and this is the same for all. Okay. 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 So this is the case, but now we can have another type of diagram in which we could draw like this. Okay, we're going to draw them conveniently because we're going to be limited by the space in which we're drawing. Let me choose like this, and then we could have something like this. L. Okay, so N, L, and then NK. Okay, so again, the positive arrows, okay, so EM and EK are above the Fermi energy. Now EL is above the Fermi energy, but EN is below the Fermi energy. Okay, that's important. So let me draw here EL clearly. Okay. Or we could have this other type of diagram. Okay. So let's draw the line here. So we could have this and like this. Okay, so this could be N, L, M, K. Okay, so remember now all the positive arrows. Okay, so now EK and EL going to be above the Fermi energy, and EM and EN are going to be below the Fermi energy. Okay, and finally we could have a whole interaction, which is just okay. Have something like this. Okay, and so we have N because they are always the ones that are coming in, and then KL are the ones coming out, but these are all whole. Okay, EM, K, L, N smaller than. Okay, so this is an interaction between poles. Okay, pole interaction. Okay, so we have all these possibilities now, and okay, so let's stop here, and the next class we're going to see now the problem of conservation. So now we're going to try to set up an expansion, a perturbative expansion for taking into account particle-particle interactions, but the main event is going to be momentum conservation. Momentum conservation and energy non-conservation, okay? Which means that we're going to only consider virtual processes. Okay, we'll explain this in the next class. Okay, so any questions here? Okay, now we're going to obtain something that's going to be meaningful. Electron-electron interactions, and this is going to generate the need to go further in the diagrammatic expansion. So we're going to obtain first the Hartree, and then the Hartree-Fock expansions, and then we're going to see that we need to go beyond this to include screening effects in order to make a convergent theory, okay? And obtain what is called the RPA approximation. Okay, well then, thank you. If you have no other comments, we meet again tomorrow to do some exercises and revise the the homework I sent.
Okay, mister.
Thank you.
Okay? Okay, see you tomorrow then.
Yeah, see you tomorrow.